Welcome to Multidisciplinary Design Optimization, lecture number 5 on optimization algorithms. So you can tell by the name that we will spend 2 lectures on optimization algorithms because of their critical role within this lecture. And today will be the first part covering unconstrained optimization problems. Here's a brief overview over what we will be talking about today. After a short introduction, we will explain steepest descent, conjugate gradient method, the modified Newton's method, quasi-Newton's method, and penalties and barriers. So in the beginning, I would like to motivate why we need numerical algorithms. You can think of a very simple optimization problem of this kind that we talked about a couple of lectures ago. And here we have a fairly simple objective function that depends on one design variable. And the structure of the function is pretty simple. We can take the first order derivative, solve for the root to obtain a necessary condition of optimality, and also plug that into our sufficient condition, part 2 of the sufficient condition of optimality, and verify that yes, indeed, it is an optimum, and we can do that analytically without problem. So let's look at a slightly more complicated problem. That we have, where we have the objective function as an analytical closed form, and when we take the first order derivative to come up with necessary conditions, it becomes more messy. You come up with all these trigonometric expressions, which you would have to set equal to 0 in order to solve for necessary optimality conditions. You come up with this expression telling you that there are several optimum candidates. And so you pick one of them and evaluate the sufficient part 2 of the sufficient conditions. Come up with this expression where you would have to plug in the value for the design variable of your optimum candidate, and it turns out that yes, indeed, at alpha 2 star equals 60 degrees, you do have a minimum because the sufficient conditions are satisfied. So by the second example, you can tell that the manual process of identifying optima is becoming increasingly tedious the more complex your problems are, and at some point you would have to rely on numerical optimization algorithms because you couldn't do it by hand anymore. So again, when problems become too complex, then you cannot solve optimality conditions analytically anymore. That also means you cannot identify candidates for optimality anymore. For black box functions, you could not even do that to begin with because you don't even have analytical expressions available. So that motivates the necessity to apply numerical procedures to solve your optimization problem. There are many ways to categorize optimization algorithms, and I will show you a couple of them to give you an overview over what is out there. So one way to categorize them is that you distinguish algorithms by the way they create candidate optima and scan the design space. So one of them would be what you can call enumerative, which says that you systematically try to cover all possible combinations of design variable values in the design space. That can become pretty expensive, and one name that is associated with this kind of approach would be full factorial, that we talked about in design space exploration. They're not so interesting for us, that's why I'm not going to go deeper into this. Then there is another class or category which you could call deterministic. Strictly speaking, enumerative would also be deterministic. But then in those deterministic algorithms, there is some intelligence embedded that avoids scanning the entire design space. So, and that intelligence pretty much relies on gradients. And to name the most important ones, gradient-based algorithms would be steepest descent, conjugate gradient method, modified Newton's method, quasi-Newton's method, barrier and penalty methods, and SLP, SQP, which we will cover next lecture. These algorithms here we will all cover in today's lecture. And then there is another class or category of algorithms which is called stochastic, and those algorithms also have embedded intelligence, but it's different from what deterministic algorithms do. In stochastic algorithms you use random numbers to generate an increment, and due to this random element you call them stochastic, whereas in deterministic algorithms this increment is computed by strict rules. And just to mention the most important representatives of stochastic algorithms, there's Monte Carlo, simulatic annealing, or evolutionary algorithms that we will very briefly cover. In particular, we will briefly talk about evolutionary algorithms next lecture. Another way to categorize algorithms is to distinguish them by the kind of optimum they're looking for. So gradient-based methods, they look for local optima, and they're very good at it. They're very fast. But unfortunately, once they found their local optimum, they are done. Whereas global optimization algorithms, they tend to be slower, but they also look at optima that are not in front of them. So they tend to be more likely to identify a global optimum. So, and to this class pertains, for example, full factorial optimization, or optimization based on random sampling, or the other stochastic algorithms where random elements are included. Because of this feature that they are able to identify global optima, they are good for, in particular, for non-convex problems. Because remember, only if you have a non-convex problem, it is possible that you have multiple optima and that your local optimum may not be your global optimum. So finally, the third way to categorize optimization algorithms, and that's the way we will be using for the next two lectures. We distinguish first by whether or not an optimization algorithm treats unconstrained or constrained problems. Today we will cover those that treat unconstrained problems. Then we distinguish between algorithms that use no gradients, that use first order gradients and the Hessian. And then we distinguish between algorithms for general problems with d-design variables and optimization algorithms that are particularly well tailored to one-dimensional design problems. We will be talking about this in a second. Those are algorithms that you would embed into other algorithms that in fact are first order methods on a high dimensional design space, but for the so-called line search you could use zeroth order methods inside essentially. And about the other algorithms I will talk about in next lecture. The general structure of the optimization algorithms that we are talking about is shown here. So we will always select some start vector, some start design vector, where k is the iteration index, and in the beginning k will be set to be 0. And then in a loop we will specify the next iteration design vector, k plus 1, by adding an increment to xk. Then there will be some convergence check, and if that is satisfied, then you abort, and if it's not, then you go back to step number 2 and repeat it until you're done and the convergence check is satisfied. So let's look at the first optimization algorithm for unconstrained problems, which we call steepest descent. The steepest descent algorithm is pretty intuitive. I'm going to go through it step by step. So the first step is where we select a start vector. And then the second step is that we specify a search direction in which we want to move our candidate design, xk. The search direction is defined in the steepest descent algorithm as the gradient of f evaluated at your current candidate design xk. And the reason for that is that the gradient gives you the information where your objective function decreases or increases fastest. The definition of the gradient is shown here. It's just the vector of the partial derivatives of your objective function with respect to the design variables. And as we are typically dealing with black box functions, we need to compute the gradient from output values. And one way to do that is that we use central finite differences, where you increase the design variable by a value delta x and decrease a design variable value by a value delta x, and evaluate the function at both design points and divide by the double of the interval size, delta x. Delta xi should be chosen appropriately. You want it to be sufficiently small that you get an idea of what the gradient really is, so that you can approximate it well. But it should be also sufficiently big that you do not end up confusing numerical noise and changes in your response function due to physical impact of the design variable. The next step is about computing the step size alpha k, because remember we have determined our search direction, but we have not determined yet how far we should go along the search direction. The step size alpha k will be computed by a 1D, one-dimensional optimization along the search direction, and it's based on the assumption that the search direction will be valid for a certain range. So it will not become immediately invalid because you have a really nasty function where the gradient abruptly changes, for example. Yeah? So we're assuming our gradient, which was the means to determine our search direction, is valid for some time or for some for some region that of your design space. So the formula says that alpha will be the multiplier of our search direction to determine our next design position. An exact optimum is not really needed because our search direction may not lead into the optimum that we are eventually looking for. So it's actually sufficient if we make some improvement and then compute the gradient again, possibly specify a new search direction and go on. So that's why we're going to perform an inexact line search. The methods that we're going to show, they are also based on the assumption that our 1D optimization problem to determine the optimal step size is a convex problem within an interval that is to be specified. You can think of this, what we're currently doing, as this optimization problem. So we're trying to minimize the objective function with respect to the step size alpha. We're going along the search direction by increasing alpha, and what we will experience, or what we will observe, is an objective function that looks like this. It's a section of our objective function surface that would depend on two design variables, and now we look at it as an objective function changing only along this line, only along the search direction. There are three ingredients that we will use, sometimes in combination, in order to perform this line search. So one ingredient is called bracketing. And bracketing says that, or what you do with bracketing is that you identify an interval that is guaranteed to contain an optimum. I will talk about this in a second. Then there is sectioning that reduces the size of that bracket. And then there's also a kind of approximation that gives you the best guess of the optimum within your bracket. Bracketing is about finding an interval that includes the optimum of our line search. And one way to identify this interval is to double a candidate interval size until is included. So when you think of a problem like shown here on the right hand side, and you specify alpha 10 as the point in the design space where your design xk is located, then you can specify a candidate interval by adding a position alpha 1,1, and then adding another interval of double size, thus creating 3 design points that you can evaluate. And if, like shown here, it happens that the design in the middle is below the design on the left and the design on the right, then you know that you got the optimum, or a optimum, in fact. So, and since we're assuming that we're looking at a convex problem, we can even assume that the global optimum of our sub-optimization problem along our search direction is included. But even if we're wrong, so let's assume it's not convex, then we at least have an optimum included. Okay, so more formally speaking, what we do is we start with an interval increment delta alpha k0. K refers to the iteration index, and by iteration index we mean the design iteration, so not the iteration within the line search, but the iteration of the outer loop where we change design vectors. And 0 refers to the first step that we do in that line search. Then we define a second, or an interval increment of the double size, and then a third increment of again the double size. And this exponential growth has the advantage that we're independent of the length, or well, the scale of our optimization problem, and we can quickly bridge scales. So assume that, just to give you an example, assume that in fact the optimum is at a distance of 1000, and we start at an increment at an initial interval of 0.1. We would need 10,000 steps until we included that optimum if we only increased our interval linearly. But if we increase it exponentially, then after even 5 iteration steps, we have a bracket that does include the optimum. So it's it's fairly fast, even if your initial interval increment is much smaller than the distance to the actual optimum. So the condition to be satisfied for an optimum to be included is this. So you want the function value to be less than the last function value, or the function value before that, and then you know that in that interval you have an optimum. If our assumption of convexity is true, then it is even the global optimum. So if your initial bracket is already, or excuse me, if the value of your initial bracket boundary is such that the design at this position is in fact larger than of your initial design, meaning that along this search direction it seems to go uphill and not downhill like you want, then either it is chosen too large and you need to reduce the initial step size, or you computed a bad gradient. When you do sectioning, you reduce the interval of interest that will initially be your bracket by moving the upper and lower limit while keeping the optimum inside. More formally, you define two candidate limits of your interval, or two candidate boundaries. One as the lower boundary plus the ratio of the interval width, and a second candidate boundary as the upper value minus a ratio times the interval width. And depending on how the function values at these at the new interval boundaries will evaluate, you choose one of them as new upper or lower boundary. And the question is, what ratio R would be most suitable? And to find out about this, I will show you two examples. In the first example, we do sectioning using a ratio of 1/3. We will compute alpha 1 and alpha 2 using the formula that I just presented. And we will be using this notation. K refers to the iteration index of the outer loop, so the loop over design vectors. And P refers to the, is also an iteration index of that inner loop within the sectioning procedure. From the lower and upper boundary, we compute alpha 1 and alpha 2. And now let's look at the function values at those limits. So you can tell by looking at this function value, and this function value, that the optimum has to be somewhere in here, in that interval. So alpha 1 becomes the new lower boundary. The upper boundary stays the same. And now we compute again two sections, alpha 1 and alpha 2. And after iteration 1, this is how far we got, and yes, our optimum is somewhere where we is somewhere in between here. There is another method that turns out to be more efficient, and this is based on the golden section. So for the golden section, the length of the interval is always the sum of the length of the two subsequent intervals. And that leads to a ratio of 0.618, so that's fairly well known. That's the ratio of the golden section. Well, and if you do this, what you find out is that by computing these two candidate boundaries, alpha 1 and alpha 2, you produce an interval for which you, by just simply adding one more candidate boundary, you can decrease the interval. So we only did 3 function evaluations. So to make it comparable to the upper scenario, we can add one more function evaluation and end up with a smaller interval that we had for this ratio of 1/3. So this method is more efficient in terms of making use of your function evaluations that you need to perform. And that's why the golden section method should be performed. So after you computed a bracket, you performed your section analysis to come up with a small range of candidate values, you may either just choose the middle as a result as an optimum, or do a more informed analysis. And the better informed analysis would be to approximate the location of the optimum within your interval using a polynomial interpolation method. Okay, and that's based on the assumption that your function can be fairly well approximated by a parabola. And using gradient information that you function values from which you can derive gradient information, or better put, you can derive the coefficients of your polynomial. So this would represent an approximate gradient, this would represent an approximate curvature. By using those function values to determine these coefficients, you obtain at a better estimate of your of the location of your optimum. So more specifically, based on the 3 points at alpha naught, alpha 0, alpha 1, and alpha 2, by just using a simple curve fitting scheme, you compute your coefficients A1, A2, and A3. Or alternatively, there's another way you can do the fit, is that you directly employ gradient information that you may have from the approximation of the gradient that you had to do in order to come up with your search direction, and from that you compute your coefficients, which would give you this kind of estimate. The formula which are a result of that fit, depending on your values of alpha and the function values evaluated at those positions specified by alpha, are this. And for the second method, read like this. So this should be pretty straightforward, and it will give you now the best guess of where the optimum along that line will be, and therefore the best possible value for your step size alpha. So this slide is to show you that, of course, when your function that you're trying to approximate becomes strongly nonlinear and is not well represented by a polynomial, then the estimate of your optimal step size could significantly deviate from the really optimal step size. Here alpha would be located at around 0.6, whereas the real optimum would be at about 0.4. And the same is, of course, true for the other approximation based on gradient information. Now let's get back to the steepest descent algorithm. We just talked about computing the step size, and now we will talk about the conversion test that will decide whether or not our iteration has to go on or we are satisfied with the result. There are several criteria that you can use or combine to assess whether it makes sense to continue the optimization procedure. Those stopping criteria can be combined into your conversion test, and the first two, they are based on an assessment whether your algorithm still makes progress or not. So the first one assesses in your output space, or more specifically whether your the values of your objective function, they still vary, they still change. The second one checks whether in your input space anything's happening. So if the distance between your next design and the previous design is sufficiently large, and if it's not, then that's an indication that it's not moving anymore, it's not making progress. Another criterion may be that you don't want to exceed a maximum number of iterations. And then finally, although I never encountered this case, there is a stopping criterion that is based on the detection of cycles, so that your function value that you got for one design you encounter again upon modifying your design, and then essentially you go in run in a loop. There is one problem with steepest descent, and that problem is related to so-called zigzagging towards the optimal solution. So when you think of this example problem here, you can tell that if you change your candidate solution along this search direction, you will not end up at the optimum. Ideally, with that line search, you find on that line an optimum and then iterate by computing the next gradient, going this way, but then stopping, because this is again the next available optimum, then change search directions, and so on and so forth. So obviously the steepest descent method is not the fastest way to get to the center of these ISO lines, and the question is, how can we increase performance of that method? And there are a couple of ways. One of them is that you just rescale the problem. And well, the advantage of this is that you can then still use the very intuitive steepest descent algorithm. The disadvantage is that you typically do not know how to rescale. But just as a conceptual idea, I'm going to show you how that can be done. So the Hessian, the second order derivative of your objective function, gives you the curvatures of your response function. And you can tell that by different curvatures, you will have a distorted shape which will promote zigzagging if you're in a bad position. And by rescaling, you can change your coordinates from x, or your design variables from x to x prime, such that with respect to the x prime space, you do not have curvatures with that are so different, but you have curvatures that are the same. So here would be an appropriate coordinate transformation that will allow you to express f in terms of x1 prime and x2 prime. And the Hessian now is simply the identity matrix. And what you did is you changed the shape of your isolines from this to this. And now the gradients will always point at the optimum. So again, the disadvantage is that in order to do the rescaling, you would need to know the Hessian. And computing the Hessian is expensive. We want to avoid that. Actually, that's something that we will address later in this lecture too. Therefore, we need yet another method. Another method that alleviates this problem is the so-called conjugate gradient method. On the right-hand side, you can already tell here in this sneak preview how it avoids zigzagging by making this first step and then not following strictly the gradient, but using a different search line that would lead it either directly to the optimum or closer to the optimum than the steepest descent method. I should have mentioned more explicitly before that this example that we're looking at here is something that is close to a problem with a quadratic objective function. But the methods we're currently discussing are not restricted to quadratic problems. They are applicable also to nonlinear problems, and the closer we get to an optimum, the better smooth objective functions can be approximated by these quadratic functions. Yeah? So these pictures here, they represent how the algorithms perform when they get close to the optimum, but they will also work when they are not close to the optimum, trying to find their way to the vicinity of an optimum. Okay, now let's get back to the conjugate gradient method. So the overall setup is similar to the steepest descent, and the key difference now is here. When we compute the search direction, we do not only use the gradient, but add something to it. And what is to be added, I'll show you on the next page. So you could think of the new search direction as the negative gradient plus something that resembles a viscous term. Yeah, so you cannot arbitrarily fast change search directions. There is some memory of the old search direction of the previous iteration step. And how strong that memory is quantified by this coefficient beta. If beta is 0, then you're left with what we had before, the steepest descent method. And the larger beta is, the more the former search direction will have influence, and the slower a change of search direction will take place, and the more zigzagging will be prevented. So you can think of this prevention of zigzagging as something good, but it may also be bad, because if you have a strongly nonlinear function, you want to be able to change search directions. So there is no universal optimal choice for beta, but there are different proposals or heuristics that you can use, which perform well in particular situations. So, and one general recommendation is the beta coefficient by Fletcher-Reeves, which is defined as this. So you can think of this as the dot product of the current gradient divided by the dot product of the gradient of the previous iteration. And with itself, these are the dot products with itself, and this is equal to the absolute value squared. So this number here becomes bigger when the current gradient becomes big, or vice versa, when you're about to converge, meaning your gradient becomes smaller and smaller, then beta will also become smaller. So the more influence the current gradient will have, and the less the search direction of the previous iteration will have. Another method, another gradient-based method that avoids zigzagging is the modified Newton's method. And again, the setup is similar. And the key difference is how the search direction is computed. Modified Newton's method is called modified because it still uses a line search, like the previous two algorithms. If it were a pure Newton's method, it wouldn't do that. It would just jump directly to the estimate of the optimum. So let's look at how the search direction is computed. When you approximate the value of the objective function at the next iteration step using Taylor expansion, you come up with this expression. The value of the objective function at the next iteration step is the value of the objective function at the current iteration step plus gradient of the objective function times delta x, where delta x is defined as the difference between next iteration step and current iteration step, or the design of those iteration steps, plus the Hessian matrix multiplied twice by delta x. So this is the high-dimensional version of the Taylor series expansion. Now the optimality condition, the necessary optimality condition, is that the gradient of f vanishes, which you can use to compute your required delta x to get there. And from this you can compute xk plus 1, which evaluates as this expression here. So if your Hessian was in fact the matrix of a quadratic objective function, then you'd be done in one step. So you could jump directly to the optimum. Well, but we're applying this algorithm to arbitrary nonlinear problems where the Hessian is only an approximation. Well, the Hessian is of course the correct Hessian, but this xk plus 1 is only an approximation of the optimum. And that's why you cannot assume that you will be done in one step. Therefore, what you do is you conduct a line search to find the best possible improvement along that search direction. So the advantage is that you do have a pretty good idea of a good search direction and you do not have zigzagging, but you don't know, again, how far you need to go. That's why you need your line search. The disadvantage of this method is that it is very expensive. And of course, if you happen to get into a position where your Hessian is singular or ill-conditioned, then you'll have problems. So there is a method that alleviates these problems, where you do not compute the Hessian directly, but you only estimate it using first order gradients. And this method is called quasi-Newton's method. So again, the setup looks like this. And for nice problems, you will reduce the number of required iteration steps significantly. And the essential ingredient of this method is here, the definition of your search direction before you again conduct a line search. So what you can tell here is that in the definition of your search direction, you'll be using a B matrix, which is an estimate of the inverse of the Hessian. And that estimate also needs to be updated. So there is an update step that comes in addition to what we saw before. How does the update work? So this is the definition of the search direction. And we need to know what a good value or what a good formula for B would be. The Hessian will be approximated by an estimate plus an update. And the update will be such that the Hessian will evolve towards the real Hessian. So in the first iteration step, you choose an initial guess or an initial estimate of the identity matrix. And then you start computing gradients, doing your iteration, updating your X vector, and also updating your Hessian. I will tell you in a second how that is done. And because inverting the Hessian is something that is to be avoided, you in fact update not the Hessian, but the inverse of the Hessian itself. So there are, again, different methods to do that. And I will show you one method, which is called the BFGS method, named after Broyden, Fletcher, Goldfarb, and Shano. They determined the Hessian as the previous Hessian plus an update that looks like this. Pretty complicated formula, and I will show you on the next page how you get there. And once you have this formula, you can use the so-called Sherman-Morrison formula to invert this matrix, the Hessian, and express it as this. And here you can identify the update for your B matrix that you need. Okay, so this is what you want to put into your algorithm. Here's your update. But for this to understand, we need to understand how we get this. And this I will show you on the next page. Imagine you are working on an objective function with contour lines that look like this. And those contour lines, your algorithm, of course, doesn't know. It can only compute at the positions xk, the associated gradients gk. And now let's think of these green circles here as contour lines that would correspond to an estimated Hessian. So if you had an identity matrix as the current estimate of the Hessian, then these would be just circles. And if you had not an identity matrix, but a matrix with a general positive definite symmetric matrix, then this would be more like an ellipse. Could be tilted and could have a different orientation from this. Okay, and this Hessian would tell you how the difference between two gradients looks like, what it looks like. So if this was your gradient at position xk, and this was your position at your gradient at position xk plus 1, then your Hessian, the estimated Hessian, would tell you how gk and gk plus 1, what their difference would be by this formula. Well, but if you make that step and end up with your line search at this position, and you find out that in fact the gradient that you observe there is different, you can use that information to update the estimate of your Hessian. And that update can be done by satisfying this quasi-Newton condition. Well, the quasi-Newton condition says that the change of your gradient should be equal to, well, actually I'd rather explain it here. The change of your gradient should be equal to the Hessian times change of your design variable vector. And this is what you can use to approximate hk plus 1. We want to approximate hk plus 1 as the sum of hk and an update that we would like to derive the formula for. And we attempt to create an update using a multiple of the dyadic product of these two vectors, delta gk, so the difference of gradients. The dyadic product is a matrix itself, it's a rank 1 matrix, and a term which is the multiple of the dyadic product of these two vectors, the first vector being hk times delta xk, and the second vector being the same, hk times delta xk. This is again a rank 1 matrix. We will justify this approach by showing that this will satisfy the quasi-Newton condition for a particular choice of beta and alpha. So we start by plugging in the expression for hk plus 1 into this term, which will, by the quasi-Newton condition, evaluate as delta gk. And plugging into hk plus 1 will give this: hk times delta xk plus alpha times delta gk transpose times delta xk. So remember, this is a dyadic product and this is a dot product, or you can think of this as a matrix times vector, plus beta times this vector in the dyadic product with this vector, which is a matrix in a product with this vector, which will also evaluate as a vector. So now you can see that if beta is chosen as this expression here, then the blue frame will be the same as this. So you can think of this matrix as being isolated times a vector which is defined by this expression. And if your beta is just minus this expression, the blue frames will add up to 0. The yellow part will evaluate as delta gk when alpha is chosen to be this value. So what you see here is the dot product between these two vectors, which is a scalar, and if you choose alpha to be 1 divided by this scalar value, then you just have delta gk equals delta gk. So by choosing alpha to be this expression and beta to be this expression, you ensure that the quasi-Newton condition is satisfied, and therefore this is a meaningful update. And using the inversion formula of the previous slide, you can conclude what bk plus 1, so the update of the inverse of the Hessian, must be. So we covered so far these algorithms. We did not talk about simulated annealing in Monte Carlo and evolutionary algorithms. Evolutionary algorithms we will cover next lecture. We did talk about also about bracketing sectioning and polynomial approximation. We're going to make a first step into the field of constraint problems, or the algorithms for constraint problems, by looking at barrier and penalty methods and briefly looking at so-called dual methods. You could try to run a numerical optimization algorithm on the Lagrangian function in order to solve a constraint optimization problem. But you would find out that it doesn't work if you just did it like this. And the reason for that is that Lagrangian functions have a saddle point at optima of the constraint optimization problem. Well, this is a saddle point in the X lambda space. And if a gradient algorithm, a gradient-based optimization algorithm would try to converge against the saddle point, it may slightly miss it and then get on a downhill track and would move further downhill and would just miss the optimum. So gradient-based optimization algorithms cannot typically find saddle points. So why do we have saddle points? We can show this by looking at the definition of the Lagrangian function and taking the second order derivatives to build the Hessian matrix. Second order derivatives with respect to the design variables x, and mixed derivatives with respect to design variables and Lagrange multipliers, and second order derivatives with respect to the Lagrange multipliers. And it's easy to see that these derivatives here would vanish. And if you have a symmetric matrix like this with 0 diagonal entries, then you will have, in general, eigenvalues, at least one positive eigenvalue and at least one negative eigenvalue. And there is a nice way to visualize this using an analogy in mechanics. So when you think of a stress tensor, which is a symmetric matrix, or can be represented by a symmetric matrix. In reality, it is a tensor, of course, so a matrix with a basis. But we will skip the basis and just look at the matrix entries, and let's look at the stress state that looks like this. Which can be visualized using a Morse circle. As this, okay? So you have on the y-axis your shear stresses, and on the x-axis your normal stresses. And if you rotated your coordinate system, you could create this stress state, which corresponds to a sigma 1 value less than 0 and a sigma 2 value larger than 0. And these two values represent the eigenvalues. And you can tell by the circle that you would need at least a negative and a positive eigenvalue. Okay, so that is an analogy that should help to understand why matrices of these form, symmetric matrices with 0 entries, have at least one positive and one negative eigenvalue. Which means for us that this point is a saddle point, and that means you cannot just use a gradient-based algorithm in order to identify this candidate of an optimum. So there are two kinds of solutions. One of them is that you do not use the Lagrangian function, but use a different enhancement of the objective function that is based on barriers and penalties, or that you use something we call an augmented Lagrangian method, or again, of course, use algorithms for constraint problems, which we will cover in the next lecture. But in this lecture, we will talk about barrier and penalty and augmented Lagrangian methods. So the basic idea of the penalty and barrier-based methods is that you turn a constraint into an unconstrained problem by adding a term to the objective function. And this term here will penalize violations of your constraints. So we choose as a general form c of x equals the original objective function plus a scalar variable r times b. This is for barrier functions. We let r be strictly be positive, and we use for the barrier either logarithmic expressions, or we take the reciprocal value of our constraint function. Well, please note, and the reason will become clear a little later, that barrier functions cannot be used for equality constraints. This is only for inequality constraints. So that's why we're only using G, J. And well, what you can already tell here is that when your x approaches the boundary of your feasible domain, then this term here will blow up. It will become pretty large, and the same here. So, and another thing to note is that whenever your r becomes smaller and smaller and eventually tends to 0, then c of x will be less and less disturbed by this barrier term away from the boundary of the feasible domain. And the solution to this problem, or the solution to the problem formulating using this objective function, will converge to the solution of the constraint problem. So let's look how that works using these diagrams here. So, well, initially you identify a feasible interior point and you choose some initial value of r. Then you select a decreasing sequence of r that tells you how quickly you want to approach 0. Then you minimize c of x by applying a an optimization algorithm for an unconstrained problem. And you take this solution as a iteration result and use that as the initial value for the next step when you change your R. And in the end of each iteration, you check whether you converged, and if not, you repeat, and if you did, of course, you abort. The disadvantage of this problem is that for very small R values, your Hessian may become ill-conditioned, and you can tell this by looking at the graph. So what's happening is that your new objective function will become steeper and steeper here in this region, and gradients may become larger and larger, and this may make your problem ill-conditioned. So this is what it looks like in a two-dimensional setting. So for a choice of an R value, your contour lines of the two-bar truss problem with A1 and A2 as design variables look like this, and then you would identify an iteration result here. Then you would make your R a little smaller, and you move towards the boundary of the feasible domain. So penalty functions work similar. They augment the objective function by, again, a value r times r minus to the power of -1 times the penalty function. And penalty functions let you enter the infeasible domain. So that's nice because this way you can also treat equality constraints. But then, of course, you may operate in the infeasible domain where you don't want to be. So that's the disadvantage. One way to find your penalty function is this expression here. So it's the sum over all inequality constraints that you have. And then for each inequality constraint, you pick the maximum of either 0 or the value of your constraint function evaluated at your candidate point. And this, of course, is positive when you're outside your feasible domain. When you're inside, you're negative, and then the maximum operator would pull out the 0 instead. So you only produce a contribution to the penalty function when you're outside the feasible domain. There's another way to treat equality constraints. So that's straightforward. You just sum up the quadratic values of your equality constraint functions, and you penalize deviations from the feasible domain equally, whether you are on one side or the other, and yeah, you do that by just summing up the quadratic terms. So again, when R approaches 0, C of x will approach the solution of the constraint problem. And similarly to what we just saw, for barrier functions, we can here look at the the algorithm that uses penalty functions, you also specify a sequence of R values that tend to 0 for your iteration index going to infinity. And within each iteration step, you find the minimum with respect to psi by solving or treating this as an unconstrained problem. And then you may end up here and tend to be outside of the feasible domain. And whenever you came up with an optimum, you check if you satisfy your convergence conditions. And if not, you repeat it. And if you do, then you're done. So again, for small r values, your problem may become ill-conditioned. And the problem is also that your intermediate results are not feasible, and you may end up with a result that satisfies your convergence criteria, but it's just not feasible. So you may have to add another treatment to get your final solution back into the feasible domain. That's the disadvantage of penalty methods. The problems you encounter using barrier and penalty functions can be avoided by using a combination of penalty functions with the Lagrangian function. And this is how it works. You add to the augmented objective function first the objective function itself, your terms that are also part of the Lagrangian function with Lagrange multipliers, and a penalty term. And then you optimize with respect to x only. So you do not treat lambda and mu as design variables. You optimize with respect to x for estimated values of lambda and mu. Once you're done, you update your values of lambda and mu and go back to the optimization. So there are two ingredients to augmented Lagrangian method. The first one is that you combine the Lagrangian function with the penalty term. The second one is that you optimize only in your x space, but after you're done, you update the Lagrange multipliers and then you repeat. This can be done for equality constraints and also for inequality constraints, but only if you also consider a so-called active set strategy. But that is something we will cover in the next lecture. So for now, just think of this method as applied to problems with equality constraints. Let me show you with this one-dimensional example how Lagrange multipliers can be updated. So on the left-hand side, you see the Lagrangian function of the optimization problem with an equality constraint, and on the right-hand side, you see our augmented Lagrangian function with a penalty term. And the optimality conditions tell you that this here should evaluate as 0. And if you apply them also to the augmented Lagrangian function, you can take this term and set it equal to the optimality condition without penalty term, and find out that lambda should be equal to lambda estimated plus 2 times r to the power of -1 times h of x, the equality constraint function. And this motivates the update scheme of the Lagrangian multiplier as lambda estimated k plus 1 is the previous Lagrange multiplier plus this term to update it. And now to put it all together, this is what the algorithm looks like. You set up your initial values, then you select a monotonically decreasing sequence of r going to 0. But in this case, for the augmented Lagrangian method, r doesn't need to go to 0 very fast. And then you minimize only with respect to x, using an unconstrained optimization method for an estimated, or for your current estimate of your Lagrange multipliers and your value of r. You solve for x star, and then you take this as the update of your candidate for an optimum. You also update your Lagrange multipliers, check convergence, and if necessary, repeat. So the advantage of the augmented Lagrangian method is that you will converge for values of r that are bigger than for penalty or barrier methods, and this way you do not comprise numerical stability as you would if you ran a classical barrier or penalty method. So let me briefly summarize what we talked about today. Today we talked about the treatment of unconstrained problems, in particular first order and second order methods. That means they rely on gradients or second order derivatives. In particular, we talked about the steepest descent method, which is the most intuitive way to use a gradient-based method. Then the first method to treat zigzagging that you encounter when you only use steepest gradient methods. That was by adding viscosity to the search direction. We talked about a quasi-Newton method that relies on approximating the Hessian using gradient information. We also talked about modified Newton's method that needs to compute the Hessian and invert it, and then does a line search along a well-chosen search direction. And then we talked about methods to do the line search, and those were zeroth order methods, bracketing, sectioning, and polynomial approximation, and also a variation of the polynomial approximation that uses gradient information, if available. And then finally we talked about the treatment of constraint problems using barrier and penalty methods, where you apply algorithms for unconstrained problems to an objective function that was augmented by a penalty or barrier term. The numerical problems that you encounter doing that can be alleviated by using a so-called augmented Lagrange method, which pertains to the class of dual methods. And here you use a combination of a Lagrangian function and a penalty term. The penalty term makes sure that you stay in the vicinity of your feasible space, whereas the Lagrangian terms make sure that you converge without R becoming too small, creating your numerical problems. So this would be it for today. I see you next week. Stay healthy and goodbye.